string theory gets a lot of criticism because you cannot prove it in a lab right now. Nobody can find something that says this theory is correct, and nobody can find anything that says this theory is wrong. So it's basically just math right now. We don't know whether it applies to our universe directly, or whether it's just some great math feat that physicists have come up with. But there are a couple things that would give it some evidence towards its cause, such as supersymmetry. What supersymmetry suggests is that for every particle that we are aware of now, there exist coupling particles that are exactly the same, only their masses are higher and their spins are different. He has the chart up there of the ones that we're aware of. Supersymmetry would double that number. And what they believe these sparticles, as they call them, sparticles are probably supersymmetry particles, what they believe they account for is the dark matter that exists in the universe. Dark matter is what we believe to be the cause of the increasing speed of our expanding universe. Without this dark matter, it doesn't make sense for it to expand at an ever-increasing speed. But with this dark matter, you can account for that.
So, are things like antimatter? Is that the kind of stuff you're talking about?
A little bit, but when they encounter each other, they don't explode like that.
Matter that actually exists in the standard model.
Yes. And these particles would actually be observable if you saw antimatter, you would blow up. So that would be good.
Wait, these particles are observable when?
Observable when? We hope with the LHC running, we might be able to find these particles, but that is a little, that is a lofty, a lot to expect from it.
Wait, you mentioned something about antimatter.
He mentioned antimatter.
Being all over the particles.
Antimatter, I'm not sure how antimatter integrates with this theory because I haven't heard of that being in the math anywhere. But another thing that could definitely give some evidence that this theory is correct is if they observed these gravitons being emitted from these colliding particles, if they could observe these diminishing in strength, then it would give a lot of evidence that string theory is at least partially correct. Because what string theory says that on our membrane in which our three dimensions exist, I'll just draw like that so you can give you an idea. These strings, these open strings, they do not travel between dimensions. They're just on our dimension like this. They can't go anywhere except for the dimensions that we're aware of. Now these open strings, because they are open, they can travel anywhere outside of our membrane. And what open strings account for is the graviton. All these are represented by open strings, and this is represented by closed strings. And closed strings, being not attached to our physical membrane, they can travel to other dimensions. And what this does is it explains why this is so weak, because it's going other places, not just where we know it. It's going into these other wrapped up dimensions, and it loses its strength in the process.
Can these open strings be in multiple dimensions at once?
Open strings?
Or the graviton strings, whatever you're talking about?
The closed strings can, yes. That's why we have some of it and not all of it. If it were true that they traveled everywhere, if they traveled only one place at a time, then it might be a little inconsistent.
So the open strings can only be in one dimension, but the closed strings can be in multiple dimensions.
Yes, these open strings can exist only in our three dimensions. I'm not clear on whether they travel through all of these dimensions at once. I imagine so, but they do not go outside of this membrane. guess that's about it. I can come back to how Einstein integrated time, but how much time do I have?
Like
5 minutes? I could probably do it in 5 minutes.
You can integrate time in 5 minutes.
Well, I have to derive it without showing it will work. Let's do it. Okay, coming back to the Pythagorean theorem. I don't know why it works everywhere, but it does. The way we know it, Pythagorean theorem looks like this. Hypotenuse squared. Now, when you add the third dimension, I'm sure some of you have done this in math classes. Squared. That gives you the diagonal of a cube. Now, you can keep doing this up to however many you want. At one point, string theory had 5 different theories. This was really inconsistent. People said, if it's a theory of everything, why is there 5 of them? Doesn't make sense. And one of them, a couple of them had 26 dimensions, 25 spatial dimensions, and this was inconceivable because these highly complex shapes would become doubly complex in this process. And also there were some that had 10 dimensions, and that's when Ed Witten came along with his M theory, which nobody knows what the M stands for. It could be magic. That's what Witten says. It could be murky because it's really complex. It can be mystical for the same reason. And also some people say W upside down makes it M for Witten. I don't believe that. That's pretty stupid. And they just call it the W theory. But anyway, coming back to this, what Einstein did is he realized that you can't integrate time into sides. These are measured in meters. Time is measured in seconds. That doesn't work. So what he did is he multiplied it by a universal constant of speed, being light. That doesn't change at all. You can use that. So time times light would equal seconds times meter per second, resulting in meters. Now, what this looks like, I don't know where all these minuses come from, but c squared times t squared minus s1 squared minus s2 squared plus s3 squared equals 8 squared. And then he also realized, from this he came up with special relativity right here. Because with this theory you can prove that when a light isn't moving and it's on for 9 seconds, this makes this all 0, this makes the t a 9, and this stays the same. And you end up with this number over here. Now what this shows is that when you're traveling past this light at 5/4 the speed of light, you will see the light on for 15 seconds. That's where he gets his relativity from.
Yeah, but you can't travel over the speed of light.
I said 4/5 the speed of light,
Okay.
sorry. You went 4/5 the speed of light, then you would see it for 15 seconds. So the closer and closer you get to the speed of light, the longer time seems. It's stretched out. That's how you're warping time. Now, what this also applies to is energy and momentum. And energy and momentum can be described as E squared over C squared minus P1, etc. equals matter squared. So it's the same thing, only with variables replaced. And of course, when you take out motion, these all disappear again. And what you get is over here. That's what you're going to end up with, and that means that matter and energy are one and the same. And yeah, that's probably not the best I could explain that but
Five stars. 6 stars. And mine didn't have finish.
why did you guys like write on this thing? You can do that later if you want.
I'll grab one and give it to you.
Okay.
Hey, Sebastian.